Yeah, maybe I can do it. All right, so a greeting to all the attendees for our space webinar. Good morning, afternoon, and good evening to all of you. And today we are really glad to invite Prof. Sai Prasad Ravishankar to give us a wonderful talk, which is titled as From Transform Learning to Deep Learning and Beyond for Imaging. So before Sai's talk, let me just give a very quick introduction to Sai Prasad Ravishankar, who is currently an assistant professor in the Department of Computational Mathematics, Science and Engineering and Biomedical Engineering at Michigan State University. So Prof. Ravishankar received his bachelor degree in electrical engineering from IIT Madras, India in 2008, and his master and PhD degrees in electrical and computer engineering in 2010, 2014, respectively, both from University of Illinois at Urbana-Champaign. So Prof. Ravishankar's interests include signal and image processing, biomedical and computational imaging, machine learning, inverse problems, and large-scale data processing and optimization problems. I just want to highlight that Prof. Ravishankar has received many paper awards, which include this one, IEEE Signal Processing Society Young Author Best Paper Award for 2018 for his paper, Learning Sparsifying Transforms, published in IEEE TIP, which is also related to his today's talk. And besides, he also won many other paper awards, including a Best Student Paper Award at ISBE, and also 2 award finalists at IEEE International Workshop on Machine Learning and Signal Processing. So without further ado, let us welcome Sai to give us this wonderful talk today. Thank you. So let me pass the time to Professor Ravishankar.
Thank you, Bihan. Can you guys verify you see my slides and hear me well?
Yes, we hear you very well.
Okay, wonderful. Hello, everyone. And depending on your time zone, it's either good morning, good afternoon, or good evening, or maybe it's closer to nighttime. So, thanks to Bihan for the very kind introduction. And so this talk is going to be titled From Transform Learning to Deep Learning and Beyond for Imaging. And if you have questions during the talk, please feel free to post in the Q&A tab rather than in the chat. And we have people on the panel who might answer those questions during the talk, or we might answer them in person at the end of the talk. And you will also have an opportunity to ask those questions in person. So before I get into my talk, I want to briefly highlight some collaborators for some of the recent work that I'll be discussing today. In particular, Mike McCann, who is a postdoc with me at Michigan State University, and Yong Long, who is a professor at the University of Michigan, Shanghai Jiao Tong University Joint Institute in Shanghai, China, as well as Zipeng Li and Suchi Ye, who are students at the Joint Institute. And also, I'd like to highlight Deanna Needle, a collaborator at UCLA, and Anna Ma, who is a former student and who is currently at the University of California, Irvine. And Mike and Suchi are also on the panel today, so I'd like to welcome them. So without further ado, here's an outline for the talk. And as the title says, it's sort of related to machine learning for computational imaging. And a lot of the recent space webinars have also focused on this issue, which is a hot topic in the community right now. And there's also interest in sort of enabling learning-based methods that can capture models with limited training data. And so in that framework, I'll be talking about this category of transform learning methods, which have existed for several years now. And these methods enable learning, sparsifying models for images in a way that's very efficient and that's scalable with respect to the problem dimensions or the data dimensions. And these methods come with nice convergence properties. And you can enforce various properties on these learned transforms like rotation, invariance, multi-layer models, or clustering-based methods, and so on. So I'll just allude to some of these and talk about how you can use transform learning in applications in image reconstruction. And you can learn these transforms in 2 different ways. So you can learn them in an unsupervised way from clean images, or you can learn them on the fly at reconstruction time and sort of simultaneously with reconstruction. So the first part of my talk would be on these sort of unsupervised or on-the-fly learning methods. And the later part, I'll talk about sort of learning these models in a supervised way for reconstruction. And in that context, I'll talk about a sort of a bi-level optimization approach that comes up and how we can solve that problem. And finally, I talk about unified learning-based approaches that sort of combine supervised learning, unsupervised learning, on-the-fly learning, along with sort of physics-based models, noise models, et cetera, in a common framework. So, and in the end, there'll be some brief conclusions. So before I get into the discussion of transform learning approaches, the introduction, I would like to show you some examples of how dictionary learning methods or transform learning methods work in different applications. So the first example is that of application is that of compressed sensing in magnetic resonance imaging. In MRI, the measurements are actually acquired in the Fourier space or K-space of the object that you're imaging. And from these measurements, you can reconstruct the image. And if you sort of have limited data or you undersample in that measurement K-space domain, then you can typically speed up the scans. That's what compressed sensing is all about. But then, you need sophisticated algorithms to reconstruct from limited data. The conventional compressed sensing approaches, which are shown over here, like the method by the famous method by Lustig, Donahoe, and Pauly, uses sparsity of the image in a wavelet domain and total variation domain and exploits that to do reconstruction. So this is sort of a non-adaptive approach in the sense that the model is not learned for the image. So the reconstruction quality may still be sort of limited in the sense that there may still be artifacts in the reconstruction. And the early works, such as in the past decade, have used dictionary learning, for example, for this problem, where this DLMRI method learns a sparsifying dictionary for little patches of the image, and it does this jointly while reconstructing the image. And with this approach, you can get reconstructions that look much cleaner and with errors that are much lower. So, so this is one example. More recent methods in this category have used, at least from my group and collaborators, have used transform learning, which is a more efficient approach for in a lot of applications. And here's an example of CT reconstruction where we have a chest volume, and I'm showing basically slices along the axial, sagittal, and coronal planes. And on the left is a reconstruction where we assume sort of the image is smoothly varying. We use an edge preserving or total variation type regularizer. On the right, we use sort of a union of learned transforms to enable the reconstruction. And so compared to this non-adaptive approach, using the learned transforms seems to remove the noise as well as improve the quality of the image features. So these examples are just to illustrate the application of these sorts of learning-based methods in imaging problems. So let me get into a briefly into what these transform models are. These are a very classical model in the signal processing community, where essentially if you're given an image X and an operator W, the model is that this operator, when applied to the image, gives an output that's approximately sparse. So this means that this vector Z has many zeros, and there's a perturbation error eta, which may be a small error capturing modeling approximations. So the image is essentially approximately orthogonal to some rows of the operator. And that's where that's why the operator sparsifies the image. And associated with this model, there's a transform sparse coding problem, which is cast in this way, where given the transform and the image, you want to find a sparse approximation. Let's say that is S sparse in this specific setting. The solution is obtained quite easily by just applying the transform to the image and then to the signal, and then thresholding that result to say the largest coefficients. And so this kind of sparse coding is quite cheap. And like I said, the transform model is very classical. It's been used in compression. It's been used in wavelet-based denoising and in a lot of other settings. So our interests are in sort of looking at different ways of learning these transforms. And the first sort of methods that I'll review are these unsupervised learning methods, where basically you have a collection of training signals or images that are given to you, or image patches. And these are the XIs. which are the columns of the training matrix X. And the goal in transform learning is to learn an operator W that, when applied to these training signals, gives an output that's approximately sparse. So Z in the problem on top is the sparse approximation, the sparse matrix whose columns have at most as non-zeros. So the goal is sort of to minimize this term called the sparsification error, which minimizes the transform sparse approximation or residual. And if you were to minimize this cost function without a regularizer, the minimizer is quite trivial, that the solution is the zero matrix for W, and which is not meaningful. So in transform learning, it's quite important to bring in regularizers that enforce useful properties. And various regularizers have been proposed in the literature. Some of these are listed here from my works in the past with Joram Bressler, and some are from my colleague who is on the panel, Bihan, and also Luke Feaster. And there have been also other methods. And for example, an early regularizer used negative log determinant and squared Frobenius norm penalty, which controls the condition number of the transform. You can sort of enforce, say, the transforms are orthogonal, or you can have a union of transforms. You can have filter bank models. You can even combine non-local sparsity models with transform learning. So there are a variety of approaches for how you can bring in what kind of regularizers you can bring in for the transform. You can also have alternative forms of the sparsity condition, where instead of the column-wise sparsity, you can have an aggregate sparsity, as shown in the last line, or you can use sparsity penalties. So in all these settings, you typically have some sort of non-convex optimization problems. So how do you solve them? You can sort of do this by using alternating optimization, where the algorithm essentially alternates between updating the transform and the coefficients in the problem. When you're updating the sparse coefficients, so you have a subproblem of this kind, in the sparse coding step, the solution is just basically transform sparse coding, where you apply the transform to the training data and you threshold the result, maybe column-wise or the whole matrix, and you get the solution. So it's just a thresholding-based sparse coding. And when you update the operator W, depending on the regularizer you use, in transform learning, you may have different kinds of problems and different solutions. For example, with the negative log determinant and Frobenius norm penalty, the solution for this problem is expressed in terms of the single value decomposition of a small matrix. So these algorithms are relatively efficient because sparse coding in particular is quite cheap. And this is just an example of how the transforms look like if you learn in this manner on, say, the patches of 8x8 patches of this classical image Barbara. So the learned transform is shown on the left, where the rows of the transform are shown as 8x8 patches, corresponding to the patches they were trained on. And the way the transform works is you apply each of these atoms to every patch in the image via inner product. So that's basically like convolving these atoms with the image, and you get outputs feature maps that look quite sparse. So when you threshold them, you get exactly sparse results with a small residual. And so essentially, the atoms of the transform act like convolutional sparsifying filters for these images, but we sort of learn them in an unsupervised way. So what can we say about the convergence properties of these alternating optimization algorithms? So I'm going to consider sort of one set of convergence results for the audience today, and where we sort of assume that we have orthogonality of the transform. So that's the regularization. In this case, basically the alternating algorithm goes between a sparse coding step, which, as I mentioned earlier, the solution is Z is obtained by thresholding, and there's a transform update step where, in this case, you basically maximize the trace of a matrix subject to these orthogonality constraints. This is related to an orthogonal Procrustes problem, and the solution is again given in terms of a singular value decomposition. And so before I state the convergence result, I would like to state some assumptions. So given the training matrix X, we assume that there exists a unitary model or sparsifying operator W star, which when applied to the training data X gives an output that's sparse. So Z star in this assumption A1 has its columns to be as sparse. We also assume an assumption called the spectral property, which basically constrains the maximum spectral norm of sparse matrices. And so Z star is basically the sparse coefficient matrix. And in this property, dk is a matrix that zeros the kth row of Z star, and dk tilde is another matrix that zeros the columns of Z star, but those columns that correspond to the complement of the support of the kth row of Z star. So, but essentially, these are sparse matrices, and you'd like to somehow constrain their maximum spectral norm. Another assumption we would make is that the initialization for the alternating algorithm is in some epsilon ball, and we'll look into characterizing this further. So the main result is that under these assumptions, you can show that the iterates in this alternating algorithm converge sort of linearly to the underlying model W star and Z star. So that's the underlying sparsifying model. So the iterates converge in a linear fashion with a convergence rate given by Q. And this convergence Q is basically given by the spectral property. So that's why we assume this is less than 1. So what can we say about this Q? Can we interpret this better? So what we can say, as shown in this corollary, is that when you have a sparsity level of 2, so 2 non-zeros per column of the coefficient matrix, and we assume, and then the rows of Z star are orthogonal, and we assume that no 2 rows of Z star have identical supports, then we can say that Q is less than 1. What does this condition of no 2 rows of Z star having identical support mean? So remember that the 2 rows of Z star correspond to 2 different filters in the transform. So all we are assuming is that there's enough diversity in the training data so that the support for the coefficients for different filters are not completely overlapping. So that's a somewhat very intuitive condition, and it's a way to interpret this Q factor. But it's only for the case when sparsity is 2. In the more general case, we can give bounds on this convergence rate, making distributional assumptions. So we assume that the support of each column of Z star is drawn uniformly and independently at random, and the non-zeros are sort of IID with a certain mean and variance. Then we can show that this convergence rate, as the number of training signals goes to infinity, will converge to this value square root of S minus 1 by N minus 1, where S is the sparsity, N is the dimension of the signal. So always we are going to assume S is less than N. So asymptotically, we are always going to have this Q to be less than 1. So that's great. There is one more thing in our analysis, which is the convergence radius. So how does that behave? What this proposed proposition says is that this epsilon must be smaller than either one of the than the minimum of 2 quantities, epsilon 1 and epsilon 2. They have some functional form, which I don't want to get into the details of. But in a broad sense, epsilon 1 captures. It basically arises from the sparse coding step, and it ensures a recovery of the support of the coefficients. And epsilon 2 arises from the transform update step. And although it has a complex form, what you can show for the distributions we talked about in the previous proposition is that as the number of training signals goes to infinity, epsilon 2 essentially converges to a constant that's only a function of S over N. On the other hand, epsilon 1 may scale as order of 1 over root S, and this may limit the effective convergence radius in practice. So what can we say about more general initializations? How does the algorithm behave? So if you look at the theorem in this case, the error in the sparse coding step, if you had a very general initialization, would scale as twice epsilon rather than epsilon. So the sparse coding error can scale up by up to a factor of 2 in the general initialization case. And in the transform update step, instead of a common rate factor Q, you may have this Q of T. And this Q of T depends on how mismatched the supports of the coefficients Z at the iteration T and Z star are. So if they are more mismatched, Q can be larger. So the effective convergence tends to be larger in this case, which can make the algorithm a little bit slower initially. So if you look at sort of the empirical behavior of this algorithm, then so we have 2 plots here. On the top is the case where the sparsity is 5 and bottom sparsity 10. And in these cases, we see that if you are in the epsilon region, then we have clear linear convergence. And if not, for other initializations, we tend to have this 2-phase behavior where initially there is a slow convergence. And once the support of the coefficients are completely recovered, then you see linear convergence. And if the sparsity is higher, then it takes more iterations to see that linear convergence, which you might expect, and also the convergence rate analysis indicates it. So, so this is just to briefly discuss how this sort of transform learning behaves and how how these methods converge. So they have really interesting convergence properties, and there's more work that can be done in this domain. And now I want to talk about how you can use them in inverse problem settings. So before I get into the sort of the gist of the matter, I want to review sort of regularized image reconstruction. And this is sort of bread and butter for much of the computational imaging community. But for newer members of our audience, basically, we are looking at trying to estimate an image X from its measurements Y. And these measurements are observed through an imaging operator or sensing operator A. And typically, the way the image is estimated is sort of by an optimization, where we have a data fidelity term, which essentially captures the imaging physics, the forward model, the measurement noise model, etc. And then there's also a regularizer that maybe enforces prior assumptions, such as image smoothness, sparsity, low rankedness, and so many other properties. So what we are going to be looking at is sort of regularizers that use transform learning. And in particular, we'll use this union of learned transforms approach, which goes back to several years ago, work with Bihan. And basically, the underlying idea is that we would like to somehow group the patches in the image into several classes, depending on the features or textures that they have. And so in this example, there are two classes, one in yellow and one in blue. And we would like to learn different transforms for each class that sparsify the features in that class. In practice, you do not know the grouping of the patches a priori, so you'd have to do this automatically while learning the transforms. And so if you think about the methods I talked about before, you could get a training data set of patches or other kinds of signals and learn this union of transforms. But what I'm going to talk about is sort of doing this on the fly, which is learning on the fly, or it's sometimes called blind compressed sensing, depending on the context. And in this case, basically, the regularizer is as follows, as shown in blue, where we assume that the patches of the image denoted as PIX, PI is a patch extraction operator, that these patches can be grouped into K classes, and in each class, there is a specific transform, WK, that sparsifies those patches. And essentially, we have the sparsification error, which is summed over the patches in the kth class and then summed over all the classes. There's a sparsity penalty, and that forms the regularizer. But the goal in this problem is that we are reconstructing the image and doing that together with finding these groups of transforms and the underlying clustering, etc. So these models tend to be adaptive to the image you're reconstructing. So that's why it's sort of on-the-fly learning. And you can solve this problem using block coordinate descent. It's a classical approach. And I want to talk about a specific interpretation of this approach for the case when you have only one cluster, so case one. In this case, the BCD algorithm essentially alternates between updating the transform W, that update is performed by an SVD, and then updating the coefficients B in this formulation, that you can do by hot thresholding, and then updating the image X, which basically is essentially a solution to a normal equation of this kind. And K denotes the BCD iteration. And so in this equation, on the right-hand side, you have the second term, which is a fixed bias term. And you also have another term, which is obtained by a set of convolutional operations. So basically, you take the previous image, xk minus 1, and you pass it through a bunch of transform filters. In the figure, that's the H filters. And you take those results and you threshold those filtered feature maps. And you take those thresholded feature maps and then you convolve them further with a set of matched synthesis filters. And then you sum these results over the channels, which is the sum over L in the equation, and you get sort of an image. You can think of this as some sort of denoiser in the model. And what the system model block in the figure is doing is it is sort of inverting the left-hand matrix in the normal equation, or maybe it performs iterative CG to obtain xk from xk minus 1. So by unrolling this block coordinate descent algorithm over iterations, you can basically think of this as sort of people think of it as a deep model where you can see these convolutional filters in every layer and sort of these data consistency or system model blocks. And with sort of on-the-fly learning, you learn these filters only from the measurements without using any training data. but you're able to do that because you can exploit some sort of optimization framework, like using this formulation. So how does this method work? Here's an example for MRI, where we have a water phantom image, and then we look at its Fourier or K-space, and we undersample this K-space according to the sampling mask on the right. And if we sort of did a naive reconstruction, we get something that's quite noisy and aliased, and the result on the bottom right is where you use the union of transforms that you learn on the fly. With this sort of approach, you can also cluster the patches, learn transforms. So how do these look like? So when you cluster the patches, if these patches are overlapping, you can also then cluster the pixels of the image. So for each pixel, you look at the patches that overlap that pixel and just do a majority vote over the cluster memberships of those patches. And that would allow you to group the pixels. So in this case, this is all unsupervised. So this is not learned to do a certain segmentation or anything like that. But what you can see is that the clusters are sort of capturing different segments of these circles. And for example, cluster 2 is capturing near horizontal or vertical segments. And the transform for that cluster sort of captures features that are specific to the cluster. And so this sort of union of transforms you can use in other applications like low-dose CT reconstruction. And this is an example where with an XCAD phantom volume, we simulated low-dose CT sinograms and then did reconstruction. On the left, in the bottom is sort of a conventional filter back projection reconstruction. In the middle, maybe I can zoom in a little bit. Suchi, can you see the zoom in? Okay, great. So in the middle, you can see the penalized weighted least squares reconstruction where you use sort of a total variation type regularizer. So this does work significantly well and reduces the noise in the FBP reconstruction. But if you do use a union of learned transforms, that noise is reduced much further, and you can also see the image features in a sharper way. So this sort of unsupervised transform learning has been used in other applications that you can look up online, our publications. So what I want to talk about next is sort of can we learn these models in a supervised way? So if we had PAT training data, can we learn these in a supervised way? And what are the different ways of doing so? So in this class of supervised methods, I'll talk about two types of methods. The first one may be familiar to some in the audience, which is sort of based on the unrolling strategy. So in this case, previously we saw sort of the block coordinate descent algorithm for the transform regularized problem. We saw this sort of figure that where we learn the filters on the fly from measurements without using training data, sort of in an iterative algorithm. Now we could as well learn these filters. Once you unroll the block coordinate descent algorithm, you can learn these filters in a supervised way. So this is work from several years ago, from 2017, where we essentially learn these filters H and G, apologies, along with the thresholds for these nonlinearities, these thresholding functions. We learn all of these so that in a supervised way, so that the error in mean square error in the network output with respect to the sort of the ground truth images, if you knew them, is minimized. And so we had adopted a layer by layer training at that time, and which seemed to work fairly well. And we also found that you could learn these block coordinate descent networks in sort of using limited PAT training data. And so here's an example where we are showing the average PSNR on the training data, which tends to saturate and level out after several layers or iterations of the block coordinate descent algorithm. And these are the filters, say in layer 1 and the corresponding thresholds. The H and G filters are not really matched to each other, so they can look different. If you use this sort of learned BCD net, as it's called, for reconstructing some other slices. So here's an example reference slice, and its K-space was undersampled by 10-fold. And in the middle is sort of the reconstruction where we use conventional wavelet and TV regularization, and on the right is where we use the trained method. And you can clearly see some of the artifacts are removed with the trained approach. And this is, like I said, there are also other methods that are now in the literature. ADMM-net is another method in this class where you unroll an ADMM algorithm and optimize its parameters. Plug and play methods are also inspired by this sort of this sort of approach. And so there are many such methods that exist, but one potential drawback of these unrolling-based methods is that you have to choose which optimization algorithm you use. So given a certain problem, you may have n different algorithms that optimize that problem. So which algorithm do you unroll and learn, and how many iterations do you unroll? So there are all these hyper or higher level choice questions that may not be straightforward always to answer. So the approach we will propose next is one where we can do the supervised learning without any unrolling. So let me introduce some notation in this problem P3. Pardon me. So we assume that we have this paired training data set. We have measurements yi, a set of them, and corresponding high quality images. These measurements themselves may be like undersampled, corrupted measurements. And we assume that we can obtain reconstructions for each measurement, yi, according to a regularized reconstruction problem. So where we find the minimizer of this data fidelity plus L1 norm regularizer term, and that we denote as X star. This X star is a function of the operator that we use for the transform sparsity penalty. And the goal in this sort of supervised learning approach is to minimize the error in mean square error between X star and the ground truth images. And you can also enforce additional properties on this operator using this regularizer J. So just like in regular transform learning, you may enforce different properties. This operator W theta may be a linear model. It could be a nonlinear model. There is much flexibility in this cost function. The underlying idea, like I mentioned, is to learn a sparsifying operator W, which is parameterized by a set of parameters theta, so that the solution of the regularized reconstruction problem is close to the true image. And with this approach, we are not looking at unrolling an algorithm, but rather we would like to learn a regularizer within the formulation that we would solve when we want to do reconstruction. So this is sort of a challenging bi-level optimization problem. Why is it bi-level? Because we have essentially the upper level cost, which is this sort of squared reconstruction error. But the variable X star in this upper level cost is actually coming from another lower level optimization problem. So that's why it's bi-level, and it makes it a little challenging to directly apply gradient-based methods. So how do we solve this problem? So we are going to consider a case where the sparsifying operator W is linear, and we will consider a denoising problem where the measurement operator is the identity. And in this case, there have been some past works that have looked at solving problem of this kind, but they typically look at using approximations and relaxations. Our approach is going to involve sort of deriving local closed form expressions for this X star in the upper level problem, and then using gradient-based methods for the upper level cost. So before I get into the method, I want to show a brief, simple example for how this sort of optimization looks like. And so this is the simplest example that you may imagine, where we have a 1D case where one measurement Y, it's only one training sample. So one measurement, a scalar Y, a scalar X you're trying to reconstruct, and X star of W, so there's a scalar parameter W, has this interesting analytical form. So it's basically piecewise smooth, but it does have points of discontinuity. If you look at the upper level cost Q of W for this problem, and it's clear from this figure on the right that Q is not only non-convex, it is also non-smooth. So even in the simplest of cases, this problem can be, can have a complex structure. So how do we solve this? So in order to go about deriving a closed form expression for X star, we are going to make this a little assumption. Let's say we have an operator W, so we are somewhere in the space of operators. And let's say we can somehow estimate the sign function C of W. C of W is basically the sign of W times X star of W. So X star is the minimizer of the lower level problem, and we assume we somehow know the sign of W X star. If we make this assumption, then we can simplify the lower level problem. So notice that we only know the sign and not the actual X star itself. So we can relax the L1 norm in this case into a linear term where this operator S plus minus, it's a diagonal matrix that on the diagonal, it has the sign pattern C that is known. And essentially, we apply this S plus minus to WX and then sum the entries. So that replaces the L1 norm. And we also need a constraint on the locations of the zeros of the vector WX. So that's what this constraint is doing, where S0 selects the locations of WX that are 0. So for this simplified problem, we can construct the KKT conditions, the Karush-Tucker conditions that would imply, that would lead to this sort of linear system of equations for finding the solution. So of the form BZ equals R, where the matrix B depends on the operator W, R depends on W, and both of them also depend on the sign pattern, which we assume is known. And we can then express X star as B inverse times R, and then pre-multiplied by a matrix PX that selects the X component of the solution, because we don't want the component that corresponds to the dual variable. So with this, so this is good. We have a functional form. We can state the following theorem, that for any sign vector C0, and for all matrices W such that the sign of W times X star is equal to C0, so all the matrices that have the same sign pattern, for all of them, the minimizer of the lower level optimization, the denoising problem, can be given in this functional form, where X star is basically given by this exact form. So in this case, so this is good in a certain sense, because there are only finitely many sign vectors, because each element of C0 can take only the values -1, +1, or 0. And so there are only finitely many values that C0 can take over the domain of matrices W. So for matrices that have a common sign pattern of this kind, then you can have a common functional form for X star. But this is not sufficient to compute gradients. So in order to do that, what we can show is that in various cases, this sign function C is actually a piecewise constant function over the domain of matrices. So this is a simple illustration at the bottom, where for the 1D case, I'm showing X star of W, and the sign function C of W is essentially a piecewise constant function. And in those intervals where it's constant, you can essentially use a specific functional form for X star, and you can compute gradients in each of those intervals. And in general, I would like to say that you can replace, if B is singular, then in the theorem, you can replace B inverse with the pseudo inverse of B, and all of the methods actually just carry forward. So now that we have this sort of local closed form expression for X star, we can compute gradients, basically just use matrix calculus, and you can compute gradients through the upper level cost and through the closed form expression for X star. And the only thing I want to point out, this is just algebra, that you need to apply the inverse of BI 2 times to compute the gradient, where BI is basically, this matrix. Let me scroll back. This matrix B, but with respect to each training signal. So it's a different one for each training signal. So we need to compute this, apply BI inverse to vectors twice when computing the gradient, and that can be done using conjugate gradients. So the overall algorithm boils down to the following, where we use these closed form expressions for X star in the upper level cost, and we use gradient-based methods, like stochastic gradient descent or Adam optimizer, or any number of other methods that you could think of for the upper level problem, and then we sort of cycle through many epochs over the training data. And each time when computing the gradient, what we need to do is we need to solve the lower level problems. For example, that can be done using ADMM. And so we don't need to compute X star itself in the lower level problem. We only need to compute the sign of W X star. So you may not need to run as many iterations of ADMM or whatnot to compute the sign perfectly. So once you have that, you need to compute these, apply B inverse to two vectors that we require in the gradient, and that can be done using CG, and then we compute the gradient itself according to this expression. So so this is sort of a way to solve this bi-level optimization problem, and we would like to show you some examples. for denoising piecewise constant images. So why piecewise constant images? Because we know that they are quite sparse. They are quite well known to be sparse, right, or sparsifiable. So in this case, so on the right, we have an example of a noisy image. We compare the denoising performance to BM3D, which is sort of a baseline method that's very popular for image denoising. And among the regularized methods, we use a TB method where we use a total variation regularizer. We also have a method with a DCT sparsity regularizer. So these are the cases where you're not learning a model. And we also have an unsupervised learning case where basically, in this case, we are learning a bunch of filters to sparsify the image, but we learn them from the clean image, from a set of clean images. And then we have the proposed method where we sort of learn on paired training data. And we can see that, so this is SNR on testing data, that we can see the supervised approach gives the best SNR compared to the non-adaptive ones, the unsupervised learning approach, as well as BM3D. If you look at examples of this sort of denoising of piecewise constant images, here's an example with BM3D, total variation, DCT, and the supervised, DCT sparsity in the supervised method. Maybe I can zoom in a little bit. And so you see that with some of the other methods, there's smudging of the edges of the image and so on, which tend to become much clearer with the supervised approach. And if you want, so this slide is showing how the filters learn with the unsupervised operator learning method and the supervised approach look like. They look quite different. For the unsupervised learning method, you need to use constraints when you're doing learning, or regularizers, and we use sort of orthogonality in this case. You don't need to enforce such constraints necessarily in the supervised case, because the cost function sort of alleviates these trivial solutions. So if you look at the filters, they do look different because they were learned in different ways. What I'm also showing are these feature maps. So basically the summed feature maps over the filters. And maybe I can zoom in again. And if you look on the right-hand side for the supervised method, these feature maps tend to be smaller along edges and more concentrated along the corners of these rectangles. So sort of they're more concentrated compared to the unsupervised case, or in a sense, they may be sparser than the unsupervised case. So you can use these methods maybe in other applications, which I won't get into in this talk. I want to sort of talk about the extension of this sort of supervised learning. So we saw two kinds of supervised learning, with one where we can do unrolling based optimization, unrolling based training, or another approach where there is no unrolling at all. Okay, so for this bi-level optimization approach, we can also extend this to sort of more general unified learning based models. So here is sort of a candidate formulation for doing such learning. Here, the lower level problem has a mixture of regularizers. So this R of X here is basically, this could capture analytical priors like edge preserving regularizers, wavelet sparsity, etc. Or it could be regularizers that come from unsupervised transform learning or dictionary learning, or this could involve on-the-fly learning of transforms. So all of those regularizers that are based on analytical models or unsupervised learning are captured in R of X. And the second regularizer term in the lower level problem is basically a network regularizer. And here we assume sort of a deep convolutional network, G theta. And this network, so it's sort of an autoencoding network, and it's learned in a supervised manner so that the network output, when the inputs are the reconstructions X star in the lower level problem, the network outputs are close to Xi, the ground truth images. So what this means is that the network regularizer in the lower level problem at the minimizer mimics an oracle regularizer. So at the minimizer, the network regularizer has the form of norm of Xi star minus G of Xi star. That's the lowermost equation. And this, because G of Xi star approximates Xi, you can say this is approximately the norm of Xi star minus Xi. So it tends to push the minimizer closer to the ground truth, which you don't have the oracle regularizer in practice because when you're trying to reconstruct Xi, but the training is done in a supervised way so that you can sort of push the minimizer of the reconstruction of the regularized reconstruction towards the ground truth. So this approach then sort of brings together different kinds of regularizers and supervised, unsupervised learning together with sort of model-based reconstruction with noise models, physics forward models, etc. So this problem compared to the previous one I talked about is definitely much more challenging, because this regularizer RFX could be substantially more complicated. It could be non-convex, it could be discontinuous. Example, it could be based on the L0 norm, quite popular in many applications, or it could be even based on another level of optimization. So it could be like a tri-level optimization. So how do we go about solving this sort of problem? So we adopt sort of an approximate iterative strategy, which we found to be quite effective in practice. And the approach is as follows. It's highlighted in blue. So first, we assume that the input to the network in the upper level problem is sort of fixed. So these inputs are the reconstructions. We assume they are known, and then we optimize the network weights, the network parameters theta, by using sort of gradient descent approaches like Adam for the upper level cost. And then once you update the network weights, say you get theta L, so L is the iteration, then you can fix the network weights and update the inputs to the network. The inputs to the network are coming from the lower level optimization problem. And so for the lower level problem, to solve that, we will make another assumption just to simplify, that the input to the network in the lower level problem is also fixed. So it's from the previous estimate. And this assumption allows you to just replace the network regularizer with a simple least squares regularizer, and you can use then existing methods for optimizing penalized weighted least squares methods for the lower level problem. So the training algorithm essentially alternates between updating the network weights and the network inputs, or solving these iterative reconstruction problems. And we call each alternation as a super iteration or super layer. So this is sort of a block diagram of the training algorithm, where we have a set of initial reconstructions, or the X0s. And these reconstructions are used to update the network weights. And then once the network weights are updated, which is the supervised module 1, then the reconstructions, the network inputs are further updated. And so that's the iterative module. And then this process proceeds. So you keep repeating this many times until you converge in a certain sense. So what we also found is that finally, at testing reconstruction time, when we are solving the lower level problem, using a sequence of networks theta L, as in training, worked better than a single network. So that's sort of an additional trick we use. So in this sort of super approaches, so super stands for supervised, unsupervised. You can use sort of different kinds of regularizers, RFX. You can use different kinds of networks for the supervised part, for the network term in the regularizer. And so we are going to consider the LODO CT reconstruction application, where we consider two very popular networks, so FPP-ConNet and WaveResNet. So FPP-ConNet is from Mike McCann, who is in the panel, and WaveResNet is from Zhongchu Liu, who is also on the panel. So there are many more methods, so we just picked these as some examples. And for the regularizer RFX, we use sort of two kinds of regularizers. One is a non-adaptive edge-preserving regularizer, and we also tried a union of learned transforms regularizer, so that you have an unsupervised learning component as well. So what we found is that we could learn these supermodels from limited paired and unpaired training data. So here's the result on the Mayo Clinic data set, where we show the root mean square error of reconstructions as box plots with different methods. Maybe I should zoom in a little bit. So on the left, we have sort of straightforward penalized weighted least squares with an edge-preserving regularizer, which seems to have the worst performance. And then we have PWLS Ultra, where we have the unsupervised transform learning, which seems to do better, but it also has the largest spread in the error. And the supervised methods seem to do relatively better, WaveResNet and FPP-ConNet. But when you incorporate these supervised methods into the super approach, you get the best performance. So super with either WaveResNet or FPP-ConNet, and with either edge-preserving regularizer or ultra regularization, seem to provide the best results. In particular, if you combine super you combine the supervised deep networks with the union of learned transforms, that achieves the sort of the best reconstruction in this in our comparisons. And these are more quantitative results in where we compare RMSE, root mean square error, peak signal to noise ratio, SSIM, and so again we can see that the super methods that combine WaveResNet and FPP-ConNet with this union of transform learning achieve the best RMSE. So this can be like 10 HU or 4 HU better than just the supervised deep methods by themselves. And they also do about 1 to 1.5 HU better than using sort of a conventional edge preserving regularizer within the super framework. So sort of combining supervised and unsupervised learning seems to provide the best image quality. And here is an example reconstruction from the Mayo Clinic dataset. On the top left is the conventional filter back projection reconstruction, which clearly is very noisy with a lot of streak artifacts, which you would expect. And then we have a penalized weighted least squares reconstruction with an edge preserving regularizer. The noise in this case is substantially reduced, but there's still a lot of artifacts. If you use either the union of learned transforms unsupervised approach or the FPP-ConNet supervised approach, both of these improve image quality over EP regularization. And if you combine them in sort of the super framework, then you get the best of both worlds, and you have the lowest RMSE for the super FPP-ConNet Ultra approach. And you can also see that some of these zoomed in regions are reconstructed much better with the super approach. And these are sort of the root mean square error plots, box plots over the testing data set. This is just to illustrate that the root mean square error converges in a stable manner for different super variations. And so the x-axis is essentially the number of iterations of training, or the number of networks theta L that you optimize for during training. So the convergence is pretty stable. And this is showing how the image quality changes as you go through the iterative process. And initially, the initial reconstructions tend to be quite noisy, and in the initial several layers, the noise is removed. Maybe I can zoom in a little bit. So much of the noise and artifacts are removed. And then in the later layers, like in layer 11, you can see that the image becomes sharper. So like the bone feature in the zoom in sort of is reconstructed better in the 11th layer compared to the 5th layer. So so that's about it in terms of results for the low-dose CT application. And I would like to now sort of move on to wrap up and give some conclusions. So first of all, I introduced these transform learning methods where you learn sparsifying transforms for different, you can learn these on images, other kinds of signals. Wherever you want to exploit sparsity as a property, you can sort of you can potentially learn transform models. You can learn them with various kinds of properties. I talked about sort of a union of transforms approach, orthogonality constraint, but there are other methods that I couldn't talk about, like multi-layer models, rotation invariance, non-local similarity combined with transform learning. And these methods can be found in the literature if you're interested. So you can learn these transforms in an unsupervised way from unpaired images, or you can learn them on the fly from measurements to do reconstruction. And so we show that transform learning has favorable convergence properties, and it provides quite high quality reconstructions in different applications. And we propose sort of different supervised approaches for learning these transforms. In particular, we looked at a bi-level supervised learning formulation for which we proposed an exact gradient-based algorithm. And we also finally discussed a unified learning-based framework for reconstruction that combines physics-based forward models, statistical models of measurements and noise, together with supervised learning, unsupervised learning of different kinds of models, and analytical image priors. So everything can be combined in this unified framework, and potentially our belief is that this sort of bringing together all these different models will enable learning better. It will enable us to learn in a better way from limited data. So so we showed results for the proposed super methods where they outperformed recent methods for the low-dose CT reconstruction application. And this research, of course, continues. The goal in our group, as well as the emerging goal in our community, is to sort of enable the models and algorithms that would go into the next generation smart imaging systems. So these systems, essentially the entire pipeline, starting from measurement acquisition to image reconstruction to image analysis, where the entire pipeline would be data driven. So the system is essentially learning from training data in the cloud or locally, as well as from instantaneous real-time inputs that it is observing in the specific system setting that it's deployed in. And it is sort of continually learning, the system is continually learning to perform measurement acquisition more efficiently and image reconstruction and image analysis more effectively. So, there's a lot more research that needs to be done in sort of in sort of building the models, algorithms for these systems, which I believe are the future for computational imaging. And as well as, there may also be necessity for improving hardware that would go along with the development of these systems. So on that note, I would like to end my talk. And I would like to thank you, everyone in the audience, for your attention. And we are very happy to take questions at this point.
All right, thanks so much for Sai's wonderful talk. Thanks. So I don't know, should we move to like Q&A directly, or maybe we need to take some question from the panelists? I'm not sure whether there's any question coming from like Jane or John. Raja, do you have any question for Sai?
Maybe I can keep my screen sharing on in case someone wanted to find it a specific slide.
Yeah, I mean, if there's no other question from panelists, I mean, I have a question, but I'm not sure whether there's a very straightforward answer, because I mean, both of us work on this compressed sensing for a while. I mean, blind compressed sensing, where mainly we are focusing on learning directly from the so-called instantaneous inputs, right? Not the external corpus. I mean, I think that's what you mean by training data here. But we also observe that combining the two, learning from both the training data, external training data, as well as the internal instantaneous inputs can benefit, maybe outperform using either of them. But actually, one question I have always in mind is that I think there's some cases or some scenarios where one training sources or one data source can help more. For example, like we agree that maybe if we're handling with highly corrupted data, or maybe a super yield-post problems, inverse problems, where we don't really, I mean, the so-called instantaneous input can be really bad. So we have to somehow rely on the external training corpus. I just wondering, in your proposed strategies, this kind of a hybrid approach, is there a way to somehow, intelligently balancing the two, or I mean, adaptively to kind of adjust the weighting between the two? I mean, I don't know, either by loss function or learning strategy. Is there any concern from your proposed approach?
So that's a really great question, Bihan. I mean, that's maybe I can give my take on it, and maybe Mike or Suchi, if you have anything, you can also add on. So I think that's a very important thing, the question that we can bring in information from various kinds of sources, right? We can bring in sort of these physics-based forward models, noise models, and so on. That bring, using likelihood functions, whatnot. We can bring in pad training data, unpad data, or maybe even the measurements themselves that we are trying to reconstruct can be used as some information. And so how do we sort of relatively weight these different sources of information to improve the performance of the system? That's I think a very good question. It is possible that maybe you're getting instantaneous inputs that are very, very noisy, for example, that you don't want to rely too much on, give too much weight to them, compared to, say, some training data that you collected beforehand, which, say, is much more reliable. So I don't think we have an, sort of an answer to this question. I think this has maybe sort of a practical import as well as theoretical import. So how do we handle this theoretically, or how do we have, just do this in our optimization? So my take is, if you had some prior information on, on sort of which of these sources of information are more noisy or which are sort of more reliable, maybe you can use that to, the simplest thing to do would be to tune the weights for the different models in the learning or in the reconstruction. So that is a possibility. So sort of with the unrolling based methods, maybe let me go back to the optimization problem. With these unrolling based methods, eventually you still end up with the with our classical regularized reconstruction problem, right? We have learned these models, but at testing time, so if our if the sort of the data was slightly more noisy, maybe we can still tune these parameters beta and mu or something like that. So because these are, say, a small number of hyperparameters that you can tune, but so that the network can still adapt to differing circumstances, or maybe the measurement that you got in at testing time had a different kind of artifact. So maybe you need to change even the data fidelity term. But I think it is plausible that you could incorporate them at testing time, and maybe the combination of these different kinds of models and regularizers may allow you to handle that. But I think that's just mere speculation. Maybe it won't. But I think that's a very good question and research direction. I think there's there's one advantage with this approach, like compared to the approaches where you just learn a deep network, because in that case you have to be very careful about, if your data change, which part of the network are you going to allow to adapt now or change so that to sort of transfer, right? So that is always a tricky question, and you may have to still tune a large number of weights in the network. But with this sort of with this more model-based approach, you may only need to tune a set of hyperparameters, which we are kind of used to in the community. So that's sort of my take on it. Like I said, it's still this is still unresolved, right? So there may be new conclusions as we or others work on this. Mike or Suchi, do you want to add anything further?
No, I think you covered mostly what I would say.
Thank you. Yeah, I agree. I think there's a possible approach to do that. I mean, to me, it's also an open question. I mean, I thought about this for a while, but I haven't got a really kind of a definite answer. But I mean, it's good to learn some kind of insights from you, in some recent works. All right. So shall we move to the Q&A from the audience? I mean, we do see some questions, but I think maybe Mike or Suchi has already answered some of them. But there's still several left. Maybe we can go maybe one by one. So the first one is actually from Jeff. I'm not sure whether Jeff wanna ask live. I mean, I actually unmute Jeff, but or maybe Jeff, you wanna say something to Sai? You wanna ask Sai directly?
Yeah, sure. Can you hear me?
Yes.
Yes.
Okay.
Hi, Jeff.
Yeah, hello. Very nice talk, Sai. In slide 40, easier question first. So if I understand correctly, your super approach is not a block coordinate descent, right? There's no descent guarantee here, right? It's some sort of approximate minimization method. Is that right?
Oh, yeah. For the training problem, it's sort of an approximate iterative strategy. So we don't have any guarantees yet.
Yeah. Okay. And then on slide 41, I'm just kind of curious why you put G of X star in the upper loss function instead of just X star. Isn't the goal at the end to have X star be a good approximation to X? You'll get G of X to be approximately X from the second term, but I'm just curious what the thought process is for having it in the first term.
That is a very good question that we have brainstormed about it for a while as well. So, okay, so the network regularizer term at the bottom has, this X minus G of X. And so at the minimizer, it's basically X star minus G of X star. You could make either X star approximate Xi or G of X star approximate Xi. In both cases, you would sort of learn an oracle regularizer. So, okay. But the question is, why do it this way? Why not the other way? So we haven't made that comparison yet, so I wouldn't be able to tell you why, which one is better. But in a sense, with the motivation that we are going for, both of those would allow you to learn this oracle regularizer.
Okay, I agree. But which one will you actually use as your final X hat in a practical problem? Will you use X star or will you use G of X star? Because it seems like that would be part of how you would decide which term to put in the loss function, training loss.
Right. So the way we have set it up, it is, you could use either of these, but in practice, we have observed that, both of those are not going to be the same image. But the results that I showed, we basically use the X star that comes from the model-based approach. So it's the X star of theta, not the G of X star of theta.
Okay, cool.
Because we are still looking at this eventually, once we learn a network or a model, that we are still solving this cost function in an iterative way. So if we look at it that way, then the reconstruction is still X star of theta.
Yeah. Okay, I got to run to another meeting. I want to say hi to everybody else, former collaborators on the line. Good to see you all. Bye.
Bye.
Hi, Jeff. Thank you. All right, thanks, Jeff. Okay, so yeah, I think we need to maybe move to the next question. And this is from Sandrash Ram. Same, I also allow Sandrash, you can, if you want, you can also ask live. I unmute you, I think.
Yeah, I mean, first of all, thanks a lot for the great presentation side. So my question was like more along the application lines. I mean, like great methods for actually reconstructing images, specifically in your low-dose CT image reconstruction. But can you talk about what are the final tasks that these reconstructed images are actually used for? Like, for example, is this just for someone to view, like a radiologist or a physician to just view these images once they're reconstructed, or is there a final task in terms of image analysis which happens after you reconstruct these images?
So of course there is going to be an image analysis task, but at the moment we are addressing this as purely as an image reconstruction problem. So our goal is to get images that would satisfy a radiologist who would look at them. But
okay,
it may be possible to, if image analysis is the end goal, so that's why I talked about in the end that you may be able to streamline or sort of adapt the process in a more joint way rather than individual components, then it may be, there may be a way to sort of bring in image analysis metrics that sort of, so that there is some interplay in the training between the reconstruction quality and also the metric that you use for a different task.
correct. I mean, that's the reason I was asking this. I mean, it's like, it's great to actually have methods developed like this, but then when you always use it in an image analysis application, let's say that you're actually trying to detect a tumor or segment a tumor once you've actually reconstructed these images. I mean, like, because you do compare with RMSE or PSNR as a comparison for quality of images, those are reconstructed. But then when it comes to actually the image analysis problem, I also wanted to ask, I mean, have you actually like looked at the reconstruction quality from the final task? Like, for example, let's say if it is a detection task or a segmentation task, have you looked at how the quality actually helps in terms of aiding those tasks in your work?
Yes, that is a very good point. At the moment, for these results that I showed, we have not done something like that. Yeah, but I think I totally agree with you that would be that is something that would be important, because that's whatever the end user application is. We would like to see, what a new reconstruction approach, how much benefit does it provide for the end application, and where you may need to do some additional image analysis on top of reconstruction.
Sure, thanks a lot.
Thank you.
Thank you. Thank you, Sandrash. Okay, so
to ask if Mike, did you have something else to add? No? Okay.
So sorry. So does Mike want to say something, or should we move to the? No.
Nope. We can move.
Okay. All right. So yeah, let's move to the next question. I think this one is from Adam and also. I also unmute Adam. So if you want, you can ask live.
Hi, everybody. Sai, that was an excellent talk. my question I asked before, you sort of philosophized at the end there about the role of the supervised and the unsupervised aspects, like on slide 41. To me, the question I would have is, do you really need the RX regularizer, especially if it's, I mean, it's there in my mind to help make your method more generalizable, to, like you described, to data that you haven't experienced yet. But in a way,
So the RFX, because the at least with the current approach, the last term is sort of learned in a supervised way from pad data. Maybe you have only limited pad data, for example, but if you have settings where you have more unpad data, maybe you can learn the RFX part, like a transform, more reliably, which might be useful. So, but it's at a broad level. I'm not saying that one is better than the other or anything like that, but it's just a framework to bring the advantage benefits of both of these kinds of regularizers together.
thank you. That's fair enough. I can see it being this trade-off of how much you want to learn from your data and how much you want to enforce from what you think should be in your data.
Right, right.
Thank you.
Thank you. All right, so then we move to our actually last question, and this is from our Venkata Krishnan. So similarly, I also unmute him and see if Venka wanna ask live if you want.
All right, so yeah, Sai, wonderful talk again. So in these, maybe you mentioned and I missed it, but when you do these bi-level optimizations, how accurately do you have to solve the second the second optimization, which is like a fully penalized weighted least squares reconstruction inside the loop? Does it have to be exact, or do you just run a few iterations and it's good enough?
Can I jump in here, Sai?
Yep.
See, so yeah, if you're talking about the supervised learning, the regularizer, as it stands right now, you need to know the sign pattern of the solution exactly. And what I have found in experiments is, unfortunately, that also requires you to know the solution quite exactly as well. So what we'd kind of like is if you could get to the sign pattern really quickly. If all you care about the sign pattern, you think, oh, well, maybe that's easier than finding the solution. And actually, I'm pessimistic that it's going to turn out that way. And actually, there's some work along different avenues that just try to solve the lower level problem. I mean, they're not trying to do operator learning like we are. They're just trying to solve TV problems. And they actually try to check that they have the correct sign pattern. And if they do, they've realized that they can just shortcut directly to the solution. So it would actually mean if you could get those sign patterns really quickly, you would actually have a really, really quick way of doing exact TV. So the answer is basically, while you do not need to know the exact solution, you do need to know its sign pattern. It seems like knowing the sign pattern is pretty hard. So in practice, you do need to solve them quite accurately. And that is the main bottleneck, because each gradient step you want to take at the top level requires like 1,000 iterations of ADMM or something. I mean, maybe you can do better than that if you tune, but it is like that. So training can be slow.
Thank you. Thanks.
That's enough. Okay.
Yeah, that answers the question. Thanks.
Thank you. I think that's actually our last question. So I think then that will be the end of the talk. So okay, so let me just thank Sai and also Mike, Siqi for giving us the wonderful talk and also resolve some of the questions from the audience, and also thank all the audience for attending our webinars. Yeah, I think also thank Sai for the wonderful talk. I think we all learned a lot. Okay, so I think
there's one more question that I just saw.
Oh, really?